Nuclear fusion is not a new process, as it occurs continuously within the core of our Sun. Its immense mass provides the gravitational force necessary to heat hydrogen past its ignition temperature of 13 million degrees Kelvin. At this temperature, the hydrogen molecules move fast enough to overcome both electrostatic repulsion and the Coulomb force, allowing the nuclei to collide and fuse. When fusion occurs, the resulting helium nuclei will be 0.7% lighter than the hydrogen reactants. This lost mass is turned into energy, approximately 20.4 mega-electron volts per helium atom produced. For 1 mole of helium, the energy output is nearly 2 terawatts of energy. Modern reactors use only a fraction of a mole of hydrogen isotopes such as deuterium and tritium.
Starting in the 1950s, a donut-shaped torus reactor named the tokamak was adopted as the primary reactor design. This design seeks to contain the plasma in a torus lined with very strong electromagnets to repel the reactants. While the protons are repelled by the electromagnets, the neutrons given off the reaction hit what's called a thermonuclear blanket wall, which in turn warms up water to produce steam to turn a turbine. Unfortunately, the tokamak magnetic field density in the center of the reactor is larger and causes the plasma to drift towards the outside and collide with the walls of the reactor. The containment of plasma has been compared to holding jelly in rubber bands. The tokamak design must then be operated in a pulse mode to limit this behavior. The Wendelstein 7 accelerator design proposes a solution to this problem. By using supercomputer-generated magnet geometries, the magnetic field lines are optimized to prevent the outward flow of plasma. The accelerator design is described as being much harder to build, but easier to operate. The converse is true for the tokamak. The most prominent experimental nuclear fusion reactors in the world today are the ITER tokamak project in France and the Wendelstein 7 accelerator in Germany.
So far, the longest successful plasma containment has been 6 minutes and 30 seconds from a reactor in the UK. Small perturbations cause instabilities in the plasma, while the design requires spent fuel to be vented from it, forming the primary challenges to continuous operation of a torus reactor. To turn these research reactors into a commercially feasible power plant, an energy recovery factor of at least 30 must be reached to replace carbon-based power plants. The goal for ITER is to reach a factor of 10, so both scale and efficiencies must increase before they become viable.
In theory, fusion power offers the prospect of an almost inexhaustible amount of energy and can directly replace carbon-based baseload power plants such as coal strip, while other alternatives such as solar and wind vary with the weather. Many scientists believe fusion energy will be a substantial component of the energy grid by as early as 2030. Although the process requires extreme temperatures, it is relatively safe. Fusion reactors are immune to catastrophic meltdown and run-away reactions. If a reactor becomes damaged or loses small degrees of necessary control, fusion reactions and heat generation would come to an abrupt stop. The main byproduct of this process is helium, which is harmless to the environment. Large flux of high-energy neutrons into the reactor cause the structural material to become radioactive for as little as 50 years. Although this number seems large, nuclear fission creates waste material which is radioactive for up to 1,000 years.